Hello, welcome back to Maths with Armien. In this video, we're going to look at functions, the concept of inverses of functions. Then we're going to look at the logarithmic function as an inverse of the exponential function. So we'll start off with an overview of the function concept. Then we'll do an overview of the inverse concept of a function. We will then show you how to find inverses of functions. We will then look at the logarithmic function as an inverse of the exponential function. And then, as usual in all my videos, I end off with an exercise worksheet for you to practice these concepts and skills. Let's start with the first. A function is a relationship between two quantities. If the value of the first quantity determines exactly one value of the second quantity, we say that the second quantity is a function of the first quantity. Let's look at the definition of a function. A function is a rule which takes certain values as inputs and assigns to each input value exactly one output value. In other words, for every input value, there is exactly one output value. The input value or output values, will refer to them as variables. The output is a function of the input. Now, functions can be represented in different ways. Let's look at the first one, is to describe it using words. In other words, we can use words to describe the function. Or function can also be represented by data that's provided in a table. In other words, we tabulate the data. Or it can be points on a graph. In other words, we can have a graphical representation of a function. Or lastly, a function can be defined or described by means of a formula or equation. And that's the algebraic representation of a function. Now, when we work with relations, some of these relations are functions and some relationships are not functions. So when would we know when it's a function or when it's not a function? And what are the key requirements for a relation to be a function? Now, the most important one is every input value must have only one output value, right? So if you input 3, you want one output. If you input another value, let's say 7, you want to have only one output. But if you input, let's say 6, and you don't get an output value, then it's not a function. Or let's say you input 10 and you get 2 output values, then it's not a function. We're going to look at a table, 3 tables actually, to show you how you can determine from the table whether that table represents a function or not. And to do this, I'm going to take a vending machine to illustrate that. Let's say we have vending machine number A. Here we have the input, which is the number that you input, and this is what you get out. So in other words, if I should press 1 on the keypad after I've paid, obviously, then I'll get a Coke out. If I enter 3, if I select 3, then I'll get a Fanta, right? So if we look at vending machine number A, let's see whether vending machine number A is functioning. 1, 1, 1, 1, 1, 1, 4, 1. But if I look at 5, there's no output. And remember, every input must have exactly one output. Therefore, this machine is not functioning. We can say this there. You can see this does not represent a function. Let's look at vending machine number B and see whether it is a function or not, whether it represents a function or not. So if I input 2, I get output of water. If I input 4, I get. But if I look at 1, I get 2 outputs, right? And if I have 2 outputs, it's also not functioning. I mean, if you put in 1, you're supposed to get 1 can out. Now you're getting a Coke, and so you say the machine is not working. It's not functioning. So B also, it's a one-to-many. That does not represent a function. Let's look at vending machine number C. If we look at that, look at it carefully. 7, there's one output. 5, there's one output. But if I look at 5 and 6, they give me the same output. And having the same output is not a problem, because 1 only gives me 1. Right? So C there, although it's many to 1, it's still a function, as long as the output is a 1 there. Now we're going to look at a few rules to show you from the rules whether you can determine whether that rule would represent a function or not. Look at the first one. Fx equal to square root of x, where x is greater or equal to 0. That means x can be any positive value. Let's input a positive value. Let's take an easy one first. 4, square root of 4, only one output. Let's put in a 16, square root of 16 is 4. Let's put in even a 5. Go to your calculator, square root of 5 is 2, it's always one output, right? Therefore, that would represent a function. Let's look at the next one. Let's be careful with this one. If I take an input value, let's say we take the input value of 9, right? So I have gx squared equal to 9, so gx will be, that's correct, it will be plus or minus the square root of 9. That gives me 2 output values. Therefore, it is not a function. Let's look at this one. X equal to 2. So x is always 2. Right? So x equal to 2 can be associated with any y value. Therefore, this is also not a function. If we look at fx equal to 2, this means it's a horizontal line, and a horizontal line, the output just remains a 2, right? So 0 goes with 2. If I have 7, it goes with 2. If I have 11, it goes with 2. If I have -1, it still just is associated only with one value. So that also represents a function. Let's look at the last one. Y squared equal to x cubed plus 2x squared. If I put an input value, let's say I make x a 1. So if I calculate that, I get 7. So y squared is equal to 7. So what will y be? That's correct, plus or minus. Therefore, that will not represent a function. Now let's look at the graph. If we have a graph, how can we determine from a graph whether something represents a function? Let's look at the first graph here. So let's follow now. -2 gives me one output. -1 gives me one output. 1 gives me one output, but 2, I have 2 outputs by 2. Therefore, what would this be? This is a one-to-many relation, and a one-to-many, when you have many as your output, it's not a function. Let's look at this one. If I look at 2, I have a positive output and a negative output. If I have 1, I get a positive and a negative. Although in 0, I just have 0 and I have 0, but other parts of it gives me one-to-many there. And one-to-many indicates to me that it will not be a function. Let's look at this one. Let's say if I should have 1, then the output is 1, right? Only 1. If I have 2, the output is 2. You see, this here indicates that that value is excluded. And any value between 1 and 2, I always get one output. Any value between 2 and 3, so this also represents a function. So this is a one-to-one and one-to-one. Now we're going to look at a graph and determine from the graph whether that graph represents a function or not. Right? Let's consider the first one. There we have 3 points. And if we plot those 3 points, let's see what we get. There's the 3 points there. Let's look at it now. 2, 1 output. 3, 1 output. 4, 1 output. So this is a one-to-one, and a one-to-one definitely represents a function. Let's look at the second example. There again we have 3 points, and let's plot those 3 points. Let's see what the graph looks like. 2 has 2 outputs, 2 output of 1 and 2 output of 2. 4 only, so there's a problem here. So this is a one-to-many relation, and a one-to-many does not represent a function. Now, when we have graphs, we can actually use a test which is known as the vertical line test. In other words, we'll use a vertical line to test whether the graph would represent a function. Now, if the vertical line cuts or intersects a graph always at one point only, as I move the vertical line, every time it only cuts it at one place, then that graph would represent a function. So in other words, if we take that, we're going to move the vertical line either from the left side to the right or from the right. Let's see now. Let's look at the linear relationship. So we take y greater than 0, that's a positive line. And we use the vertical line. You can see the vertical line only cuts it once. Let's take the vertical line but a negative gradient. Also cuts it once, so that's a one-to-one. Let's take a line where the gradient is not positive nor negative, but it's 0. So we have the horizontal line. Remember the one we had earlier, fx equal to 2. So let's use the vertical line. The vertical line cuts it once. So that one there is also cuts it once. So it's also a function. Let's take this straight line. Here we have a gradient that is undefined. So there we have a vertical line, x equal to c. Let's say x is 5, it will just be a vertical line there. Let's just follow the vertical line there. Can you see how many times the vertical line cuts it infinitely many places there? Therefore, the output is not a unique output. Therefore, it will be not a. Let's consider the quadratic relationship. Y equal to ax squared plus bx plus c. Let's look at the case where a is greater than 0. In other words, we have a shape like that, and this particular shape, as you can see, is a parabolic shape. And let's apply the vertical line test. Cuts once, always cuts once, therefore that would represent a function. Let's take the case where a is less than 0. So we have this shape there. Let's apply the vertical line test. Always cuts once as well. So this quadratic relationship represents a function. But let's look at this version of it. Here I have x equal to ay squared plus by plus c. You see there y is the subject, here x is the subject. And the representation of that will be this representation here. Let's apply the vertical line test to that graph there. As you can see, it cuts twice, right? And if I have this version of it there, let's use the vertical line test again, also cuts twice. Therefore, this here does not represent a function. Let's look at the following quadratic relationships. In this case here, we have a restricted range, y greater than 0. You only want the y greater than 0. Let's check whether that represents a function. Always cuts it at one place. You can even have this one where we have y less than 0. You can see there's y less than 0. Let's look at that. And there we always have a one point of where it cuts. So this here also one-to-one. So this also represents a function. Let's look at the hyperbolic relation. There we have a hyperbola. Let's apply the vertical line once, still once. Therefore, it's a one-to-one. Therefore, this would represent a function. Let's consider the exponential relationship. And here we have the form y equal to a times b to the x plus c. Let's consider the first case where b is a value greater than 1. For example, it could be 2, it could be 3, it could be 1.5, it could be 2.5, but always a positive number. And this would be the representation of that exponential relation, right? If I have a value where the base is greater than 1. Let's apply the vertical line. See the vertical line there? It only cuts once. So that will be a function. Let's take one where the value of b lies between 0 and 1. No negative values. So I could have 0,25. I could have a third. I could have 2/5, etc. So this one here, there we have that exponential relationship. And let's look at it. Vertical line always cuts once. Therefore, exponential relationships are, let's consider the circle relationships. X squared plus y squared equal to r squared. From your analytic geometry, there you know that that's a circle. Let's apply the vertical line. See there? Let's follow. Can you see the vertical line? Cuts it at two places. It has a positive and a negative. So the circular relationship here, using the vertical line test, shows us that it does not represent a function. Let's look at the semicircle. In this case here, the y is greater than 0. Y is positive, so we have the top part of the circle. Right? The semicircle is the top part of the circle. Let's use the vertical line. Again, you see it only cuts once, so that would represent a function. But instead of taking the top or the bottom, let's take this version here, x equal to negative the square root. And this is the left side of the circle, right? And here the x values are negative. Let's apply the vertical line. And you see in the case of the vertical line there, that shows it cuts more than once. Therefore, it will not be a function. Okay, let's see there. Can you see? So it's the same. These two are the same. This one here does not represent a function, and this one here also does not represent a function. But when I have the top part of the circle, the semicircle, or the bottom one there, that would represent functions. Now let's look at the concept of inverse of a function. Let's look at a real life situation. Let's look at the following actions there. First of all, open the door, enter the room, walk towards the seat, sit on the seat. Right? So if we look at that, we've done these actions in this order. First, open, then enter, then walk towards, and then sit. And if we want to reverse it, that is what we have to go the other way. So the last action must be done first, and the first action will be done last, but we'll reverse the actions. So can you tell me what's the first thing we'll do? That's correct. What's the opposite of sitting on the seat? That's correct. Stand up from the seat. And the next one, walk towards the seat. That's correct. Walk away from the seat. Enter the room. What's the reverse of that? Exit the room. Open the door. That's right. Close the door. So there we have the operation that took place this way, and there we have the reverse operation. We can also call it the inverse operation. The last action becomes the first action, but we just do the opposite of it, right? The first action became my last action, but instead of opening, the opposite of opening would be closing. The opposite of entering would be exiting there. And we have many situations like that. Let's see what we mean by inverses of functions. There we have input value x, then we have the rule f, and then we have the output fx. Now the input values there are referred to as the domain of the function, and the output values are referred to as the range of the function. And this here is the rule that we have there. Now, if you want to do the reverse, we're going to take our output value, which is fx, and now reverse the process. See the inverse, reverse the process, and then we'll get back to our input value. So the range of my function becomes the domain of my inverse. And the same way, the domain of my function becomes the range of the inverse there. Now, just look at the notation that we're going to use for inverses. If we write down f with a -1, we read it as inverse of f. Don't read it as f -1. Note that 2 with a -1 is actually 1 over 2. 7 with a -1 is 1 over 2. But if I use the f with a -1, I do not write it mean that it's 1 over f. Right? So when I work with functions, f -1, if I write a f -1, it doesn't mean 1 over f. This, remember, if in functions, we read this as the inverse. So the inverse of f is not 1 over f. You've also seen in trigonometry, when we talk about the inverse of sine, this is the function that we have, inverse of sine. For example, if you have sine of 30 degrees, the output is 0,5. So if I take the inverse of sine of 0,5, then I end up back with my 30 degrees. And you know, this here is not sine -1. We read that as inverse of sine or arc sine. Now, just look at some of our basic operations that we've been working with since we started with mathematics at school. Addition. There's addition. What is the inverse of addition? That's correct, subtraction. And if I take subtraction, what's the inverse of subtraction? That's correct, it's addition. So addition and subtraction are inverses of each other. Multiplication, and there we have division. And division then will, inverse will be multiplication. If we have a power, let's say for example I've got x to the power 3, what will the inverse of that be? That's correct, cube root of 3, right? Or if I have square, it will be square root. So a power, the inverse would be a root, and a root again, the inverse would be a power. If I take trigonometrical functions again, sine, cos, and tangent, I can get inverse of sine, or inverse of cos, or inverse of tan. Right? Remember, inverse of sine is not 1 over sine. 1 over sine is the same as, you did it in grade 10, cosec, that's correct. Then we're going to work with a new function here. This is the exponent is not new, but the inverse of an exponent is we're going to use that and refer to it as the logarithmic function. In one of the units, we're specifically going to look at this new inverse. These are all these inverses you did at primary school. Then when you started at high school, you did some powers and roots. And then from grade 10 onwards, you started working with the trigonometric functions there as well. Let's consider a table and show you how we can determine inverses. Let's look at this given table. Let's look at it there. These are the input and these are my output values. So this information is given. Now, if we want to determine the inverse of this relationship, then we'll have to interchange the input is going to become the output and the output is going to become the input. Let's look at that. Right? So my input values became my output values. And my output values there become my input values. Now let's look at this. This you can see 1:1, 1:1. Is this all a function? 10 only gives me one output, 12 gives me one output, 14 gives me one output, 16 gives me one output. Therefore, this is 1:1. Therefore, that is also a function. So to determine inverse, you can just interchange the input and the output values, the corresponding input and output values. Let's look at another table. Let's look at this table here. This is a function, 0, only all of them. This is a 1:1, 1:1, 1:1, 1:1. Let's just determine the inverse of this relation. So the inputs are going to become my outputs. You can see there. And then my outputs are going to become my inputs. Now let's look at this. 1 has an output of 0. 0 has an output of 1. But then 1 also has another output. So if I look at that there, I have 1 and 0 and 1 and 2. 1 and 0 and 1 and 2. So that is a one to many. 1 gives me 2 possible outputs. Therefore, what do we know about this inverse relation? That's correct. It is not a function. Let us consider some graphs. Let's take the function f. There we have f. Let's see whether it represents a function. As you can see there, every x value is only associated with one y value. 3 with 7, 2 with 5, 1 with 3, and 0 with 1. Now if we want to find the inverse, we have to change all the x's to the y's. In other words, we need to reflect this into this line y equal to x. So there I have 3 and 7, so I'll get 7 and 3. So let's plot those points. There's 7 and 3, and that was 2 and 5. This is 5 and 2, and that was 1 and 3, and this is 3 and 1, and that's 0 and 1, and that's 1 and 0, right? So now, f was a function. Let's look at the inverse now. See, there's the inverse. So now we need to check the inverse. 1 y, 1 x, 1 y, 1 x, 1 y, 1 x, 1 y, 1. So the inverse there is also representing a function. It's 1 to 1, so it also represents a function. Let's look at another graphical representation. There we have a function f. And this is a parabola. And you can see this here represents a function, right? A vertical line would cut it only once. Now let's take these points here, and we're going to reflect it in the line y equal to x. That means the x and the y coordinates are going to be interchanged. 2 and 5 becomes 5 and 2. 1 and 2 becomes 2 and 1, etc. So let's plot those points, and we can just check some of them. There we have it. Let's see here. There I have negative 1 and 2, so I need 2 and negative 1. There I have negative 2 and 5. I need 5 and negative 2. So that's the inverse of that relation there. Let's just join those points, and we see that we get, there we have it, right? So we know this white here is a function. Let's check whether the inverse is also a function. So if I look at that using the vertical line test, we can see here that the vertical line cuts it more than once. Therefore, now let's look at a test that can be used to determine whether the inverse of a function will again be a function. And this is known as the horizontal line test. So if a horizontal line intersects a graph always at one point only, then the inverse graph, right, will represent a function. So let's look at this example here. Is this a function? Right? So the vertical line shows me, let's just test with a vertical line. Yes, vertical line. And if I take now a horizontal line, also cuts it once. So a vertical line cuts it once, and a horizontal, therefore the inverse would be a function. Let's look at this one. Let's use the vertical line test. Following the vertical line, once, always once, right? Let's look at the horizontal line. Twice. So the horizontal line cuts it twice, therefore the inverse is not a function. Now next we're going to look at showing how you can find functions but algebraically. So there's a general procedure we recommend that you follow. First of all, the most important part here is the input and the output must be interchanged or swapped. In other words, x becomes y and y becomes x. To help here, I'm putting the x in this blue and the y, the output values, in yellow. So we can just follow that there. Then we're going to make the y the subject of the formula. And then once we have the subject of the formula, we'll be able to get it in the form, the inverse of f. Right? Just to remind you again, we're going to use this here. If there was addition, it will become subtraction. If there was division, it becomes multiplication. If there's a power, it will become a root. So remember what we had this earlier? I've just reminded you again, we're going to use that. Let's look at some examples. In this example here, we have the rule fx equal to 2x minus 3, and we want to determine the inverse rule. So let's see, how do we start? First of all, we have to interchange the input and the output value. So the x becomes a y and a y becomes a x. So let's just look at the color coding there. I have x in blue and y in yellow. So we now interchange them. So the y becomes a x. You see the y became an x and the x becomes a y. Next, we want to make y the subject. So to do that, it's much better writing 2y minus 3 and put equal to x on the right hand side. Now we have to do the inverse operations. Instead of subtracting, that's right, we add. Instead of multiplying by 2, we divide by 2. And now we can just write it in the required form, the inverse of f of x, and there we have x plus 3 divided by 2. We just compare it to the original. We can see there we have subtract 3, and there we have the opposite, plus 3. There we have multiply by 2, and there we have divide by 2. Let's look at another example. Here we have fx equal to negative 2x squared plus 3. So what's the first thing we do? That's correct. We interchange the x and the y. So we're going to have x in blue. So there's it. There's the x and the y. So the first thing we do, we interchange it. So that becomes negative 2y squared plus 3 and y. So we say equal to x. Now we must make y the subject. In other words, we need to take negative 2y squared. So instead of adding 3, what do? The inverse, you subtract the 3. Instead of multiplying by negative 2, we divide by negative 2. Instead of squaring, we find, and remember, it's plus or minus the square root. So there I've got the inverse relationship there. And there's the inverse relationship. And you can see this inverse relationship gives me two outputs. Therefore, this would not be a function. Let's just look at this again. You see, originally we had plus 3. There we have minus 3. There we have square. There we have square root. There we have times by negative 2. There we have dividing by negative. Let's look at another example. Let's look at the rule fx equal to square root of x minus 4, and we want to determine the inverse rule. So we start as usual, interchange x and y, and just I'm using the same color coding. So I take my given rule, y equal to square root of x minus 4. I now transform it, and then that becomes square root of y minus 4 equal to x. Better to put the x at the end there, makes this next step much easier. So I have there. So now there are two operations, subtracting 4 and square root of 4. So which one do I do first? The one on the outside, which is the square root. So what's the inverse of operation of square root? That's correct, the square. And the inverse of subtraction, that's correct, is addition. So I end up with x squared plus 4. And if we now write it in the required form, inverse of f of x, and I get this. Now let's just compare again. There I've got subtracting 4, there I'm adding 4. There I've got square root, and there I have the square. So I know definitely I have done that inverse. Let's look at another example. In this example here, you're going to be using a exponential rule, 2 to the x minus 3, and we want to determine the inverse rule for that. So as usual, remember the first one, we have to interchange the x and the y. So let's do that, same color coding. So that becomes y is equal to 2 to the x minus 3, and that will become 2 to the y minus 3 equal to x. Right? Let's just have it that again. So now, there are two operations. There's the exponent and there's subtracting 3. What will we do first? That's right, the subtracting 3 becomes adding 3. And now we've got something new here. 2 to the exponent y. Now to make y the subject, remember we said from that table, the opposite of exponent is logarithm. So here the base is 2, so I'm going to take a logarithm with a base of 2. And that we write as, so I have to change it from exponential to logarithmic form. So that becomes y, and that becomes log. If the base is 2, let's put the base 2 there. And then just open a bracket, and then you have x plus 3. Okay. So then we write it in the required form. And let's just compare that. We were subtracting 3, and the inverse rule had plus 3. There we have an exponent, and the inverse rule has logarithm there. But the base is 2, and that base still remains 2. Let's look at one more example. In this case here, we have a rule fx equal to log of x to the base 4, and we want to determine the inverse for that rule. Let's start as before. We're going to interchange the x and the y. Let's use the same color coding. So there we've got y, this is given, y equal to log of x to the base 4. And that we now change, that becomes log base 4 of y equal to x. You can also read it like that, log base 4 of y equal to x. Right? Now we want to change the subject. So to be able to change the subject here, because I have log form, we want to change it to exponential form. Let's just recopy that again there. Log base 4 of y equal to x. So I want to get rid of that log base 4. So the inverse of a logarithm becomes exponent. What's the base here? 4. So the exponent will have the same base, and that just becomes y equal to 4 to the x. Actually, you can go directly from there to there. You don't have to do all these steps in between. Okay, so let's write it in the required form. And now let's just see. You see you have a logarithm, and you just have to change it to exponent there. In this unit, we're going to look at the logarithmic function and looking at it as the inverse of the exponential function. Let us just briefly recap what we have learned about exponential functions in grade 10 and grade 11. Right? This here is the general form of the exponential function. We have a times b to the x plus c, and it's important here, a can never be a 0. Then we have, and b must always be a positive value, right? The b here will indicate whether the graph is going to be increasing or decreasing, and the c there will indicate to us what the asymptote is going to be. So let's see, y equal to c, that gives us the asymptote, right? And the domain of an exponential function is always x, an element of the real numbers. And the range there will depend on the asymptote and also on the value of a. So in this case here, if a is positive, the range there will be y greater than c. Now let's look at the case where b is a value greater than 1. Right? In other words, we did this previously. When b is a value greater than 1, for example 2, 2,5, 3,1. Right? So a value greater than 1, that indicates to us that we have an exponential function that is, and what is this? It's increasing. That's an increasing exponential function. The asymptote in this case is c, so there we've got the asymptote there, right? And you can see the range here will in this case be greater, because I have a positive number, so the graph will go that way. Okay, that's an increasing function. If b lies between 0 and 1 again, then I'll have a exponential function that will be, in this case, it decreases, right? And the domain is still real and the range is still y greater than c. Now let's determine the inverse of the exponential function, right? Defined by fx equal to a to the x. And we're going to look at the case where a is greater than 1. That means we're going to look at the increasing exponential function. So let's have the increasing exponential function there. And there we have 4 points that are plotted there. I can maybe see this is 2 that goes with 4, and 1 that goes with 2, and 0 with 1, and 1 with negative 1 with a half. Okay. So if you want to determine the inverse, we need to reflect that in the line y equal to x. In other words, the x and the y's must be interchanged. So let's interchange that, each of those points. So this point here is 2 and 4. So now we look for 4 and 2. This one here is 1 and 2, and there we have 2 and 1. And this one 0 and 1, so we have 1 and 0. You can see that's on the y-intercept. This becomes an x-intercept. And this is negative 1 and a half. And then we plot that half and negative 1. And if we join those points, and there we have the inverse curve there, right? And you can see the f is a function and the inverse is also a function using the vertical line test there. Now, f is an exponential function, right? There's fx defined by fx equal to a to the x, and the defining equation for the inverse is known as a logarithmic function. And this, if the base is a, we have logarithm base a. So this is the exponential and that is the logarithmic. Let's compare some of their properties. The domain of the exponential is x, an element of the real, where the domain of the inverse, you see the domain of the inverse is only positive values, therefore x is greater than 0. The range of the exponential is y greater than 0 because the asymptote is 0 there. And the range of the inverse again is y, an element of the real numbers. Just see there, there is x, an element of the real, and here is y, an element of the real. Here is y greater than 0, here is x greater than 0. The asymptote here, this one has the exponential has a horizontal asymptote. So the logarithm would have that's correct, will have a vertical asymptote. This horizontal asymptote was y equal to 0, and the inverse one has x equal to 0. Now we're going to look at how to sketch a logarithmic function. Let's take this example. Sketch the function f defined by fx equal to log base 2 of x. Now it's advisable to set up a table. Although you want to sketch the logarithmic, it is easier to set up a table for the exponential. And to set up an exponential table, we always make use of the most important numbers in mathematics, which are, that's correct, 0 and 1. And we also use negative 1. If you use these three values, you can always use this to draw a sketch of an exponential function there. Let's compute those values, and those are the values we get there. But because we want to find the logarithm, which is the inverse, we swap the domain and the range. And if we do that, so there's the, you can see the range becomes my domain, and my domain would become my range. Now we're ready to plot the curve. But if you want to plot these curves, any type of sketch there, although they say a sketch, try to set it up so that you have some decent scale there. Maybe you can use centimeters along your x-axis and use the lines of your page for the y-axis, unless the question paper provided you with a grid on which to draw that. So let's plot those points now. And those are should be very easy to plot that. So if we plot those 3 points, and there are the 3 points there. Let's see there. This is 0, 5 and -1. That's 1 and 0, and that's 2 and 1. And now we can join those points. And there we've joined the points there. And there's my exponential, my logarithmic curve there. And it's important here that you do indicate what the values are. If you don't indicate the it in coordinate form, at least have there 2 and 1 so that the examiner can see what the coordinates of each of those points are. You can't just leave it without the points there. Let us look at one more example how to sketch the inverse of a function. In this case, let's take the function with the rule fx equal to -2x squared. Okay, so we will need to set up a table, and as before, suggest using 0, 1 and -1. This can always be very helpful to sketch any type of function there, especially these ones relating to inverses. Then you compute the corresponding output values. Now, because we want to determine the inverse of that function, so we'll have to interchange the domain and the range. So let's interchange the domain and the range. So the -2, 0 and -2 becomes my domain, and the -1, 0 and 1 becomes my range. So we set up a system of axes. Again there, set it up neatly. You plot your points. Let's plot those 3 points. There's at 0 and 0, -2 and -1, and -2 and 1. Now we can join the points, and there we have the inverse there. Okay. Now we're going to look at an example that will assess all these concepts that we have done thus far. Here we have 2 functions f and g with their defining equations. The one is half to the x, and the other one is x squared minus 4. This here is that's correct, an exponential, and that one is a quadratic. So we want to determine the domain of the inverse, and there's a few questions, and we're going to look at each of these questions individually. Let's start with the first one. Let's look at the first one here. So just copy the defining equations down there so we don't have to refer back to the previous slide. Write down, see the write down, so this should not be complicated. Write down the domain of the inverse of g. So we don't want the domain of g, but of its inverse. Now the domain of the inverse is the same as the range of g. What would the range of g be? That's right, you look at the y-intercept there. The range of this one is y greater than or equal to -4. So the domain there would be x greater or equal to -4. We can either write it in this notation or we can write it in interval notation. I would recommend the interval notation. Then we have to find the range of h. Now there's no h there, but they tell you what h is. H is the f, and then you have fx plus 1. What does this mean? Plus 1 means that's right, it's moved 1 unit upwards, right? So in other words, if I know the range of f, I just have to transform the range of f. So what is the range of the f? This is an exponential, so its range is, that's right, y greater than 0. So I have to take the range of f. The range of f is y greater than 0. But because I'm shifting it 1 up, I'll have to take the range of h, then will be y greater than 0 plus 1. So that becomes y greater than 1. Or we can just say y is an element of 1 up to infinity. Right? So that means it was 1 up, so the range has just been adjusted there. In this case here, we want to find the inverse rule for f. So there's f, let's find the inverse. And what do we see? What type of equation? That's right, an exponential. And an exponential is going to become, that's right, a logarithmic. So this is an exponential, and I can, if I want to, I can change it, my x's and my y's, and then I can get that in logarithmic form. So y to the x become log base a half of x. Right? You can go straight from there to there. Now let's look at the other three sub questions. There I've got the equation there again. Here they ask us to draw the graph of the inverse of g. So I must take g. So we don't have to get. They didn't ask us here for the equation. They want the sketch. And how did we say we're going to do that? That's correct. You set up a table, and your table here preferably would be -1, 0, and 1. If you try always to make use of that, right? It should always help you. So if we compute the output values, those are the output values. But that's the table for the G. If we want to draw the inverse, we need to invert it. You don't have to redraw the table. You can just see that will be -3 and 1, -4 and 0, and -3 and 1. But let's just complete it. So now we're ready to sketch the graph. So I just plot the point there. -3, can you see? -3 and 1, -4 and 0, and -3 and -1. And then you can draw the graph there. You know, there you've got 3 points. They didn't say that you must indicate the intercepts on the y-axis there. In this case, it comes out exactly as 2 and -2. Then let's look at the next question. Explain why the inverse of g does not represent a function. How do we check whether something is a function? Yes, you can use your vertical line, and you can see if I draw a vertical line anywhere there, how many times does it cut? It cuts twice. That means it's not 1 to 1. It's actually 1 to many. It's 1 to many. That is why. You see, that's the reason. It's 1 to many. Okay? Or you could say that the vertical line cuts the graph at more than one place, therefore it is not a function. But this is the easiest way to write it. 1 to many. Now let's look at the last question. How can we restrict g so that the inverse will be a function? One way to restrict it is to restrict the domain. You can either take the right side of the function or the left side. In this case, x greater or equal to 0, or you could write down x less or equal to 0. Okay, so you can give any one of the two here would be acceptable, either on the right side or on the left side there. Now, before you actually start with the exercises in this worksheet, I suggest that you first go back and try to do the examples that we've done in this lesson. First, try to do it on your own. Look at the question, try to solve it, and then once you've done it, compare it to the solution. So go through all of them and even go through some of the slides just to make sure you understand the concepts and the procedures and the skills that we've shared there. Now in this first question, here, there are a number of rules and you have to determine the inverse rule for each one of them. Then in the next question here, there are 4 graphs and you have to, on these graphs, draw the inverse graphs for each one there. Question number 3, there are 2 functions. One is a quadratic and the other one is a linear, and then there are some questions relating to those 2 graphs there, finding the inverses, sketching the inverses. The same here. Here we have 2 other functions. The one is a linear again and the other one is an exponential. This one here we have an exponential, and then we have some questions based on that exponential graph. Question 6, there we have again an exponential with a quadratic. In question 7 here we have some equations, one log equation, and then 2 log inequalities there. And then the last question here Here we have a log function with a base 4. You have to find the domain range for it, find the equation of the inverses, find the asymptotes, and then there's some questions with regard to reflection, and there's some questions with regard to translation, and then here we have a question here to do with the transformation from log base 4 to the exponential there. Well, thank you very much for listening to my lesson, and I hope it helped you. And I would also like you to view the other videos on grade 12 CAPS mathematics, and please subscribe to my channel. Thanks.